Let me state the theorem and paraphrase what the professor just told. Let C1 and C2 be real numbers. Suppose that x square minus C1x minus C2 equals 0 has two distinct roots x1 and x2. Then the sequence an is a solution of the recurrence relation an equals C1 an minus 1 plus C2 an minus 2 if and only if an equals alpha 1 x1 to the n plus alpha 2 x2 to the n for n from 0, 1, 2 and so on, where these alpha 1s and alpha 2s, they are constants. Though the theorem might seem to be very tough and difficult to remember, it is actually very simple. So, given this quadratic equation which has two distinct roots x1 and x2, then this sequence an, it will be a solution of the recurrence relation. And of what form is this recurrence relation? It is some constant times an minus 1 plus constant times an minus 2. And the solution is of the form alpha 1 x1 to the n plus alpha 2 x2 to the n. These x1 and x2, as you remember, are the distinct roots of the quadratic equation. Now, let us see how we can apply this theorem in a few problems. If an is given to be 3 into an minus 1 minus 2 times an minus 2, then what is the solution of this recurrence relation? a0 is given to be 1 and a1 is given to be 2. So you have to find the solution of this recurrence relation. Now, so I am going to write now the quadratic relation of this, or the characteristic equation of this recurrence relation. It is r square minus 3r plus 2 equals 0. How did I get this? As you see, the constants here C1 and C2 are 3 and minus 2 respectively, and hence substituting that in the quadratic equation, I get r square minus 3r plus 2 equals 0. Now, how can I solve this? I can solve it using the formula minus b plus or minus b square minus 4ac square root by 2a. Now, solving this, I will obtain the two roots. So, let me substitute for abc. So, I will get 3 plus or minus root of 9 minus 8 by 2, and this happens to be 3 plus or minus 1 by 2, which is 2 and 1. So, 2 and 1 are the distinct roots of this quadratic equation. So, I can write an as alpha 1 into 2 to the n plus alpha 2 1 to the n, right? Now, if I substitute n as 0 in this recurrence relation, what will I get? a0 is anything to the n is, anything to the 0 is 1, and hence I will get a0 is alpha 1 plus alpha 2. And if I substitute n as 1 in the recurrence relation, I will get a1 as 2 alpha 1 plus alpha 2. Right? Now we have these simultaneous equations with us, but according to the initial condition given, we know that a0 is 1 and a1 is 2. Right? So 1 is equal to alpha 1 plus alpha 2 and 2 is equal to 2 alpha 1 plus alpha 2. Now, when we solve these simultaneous equations, we see that alpha 1 is 1 and alpha 2 is 0. So, I can substitute these values back in the recurrence relation. So, what will I get? an is equal to alpha 1 2 to the n plus alpha 2 1 to the n. This is the equation. Now, if I substitute for alpha 1 and alpha 2, I'll get it as 1 into 2 to the n plus 0 times 1 to the n, and hence your final solution will be an equals 2 to the n. So, this is the solution for the recurrence relation that we initially started with.